Welcome to this video presentation on conduction heat transfer. Today we'll be working through example 3, which involves heat transfer through composite slabs with a heater in between. This slide illustrates the physical setup of our problem. We have two slabs, slab A and slab B, with a square plate heater inserted between them. Heat, denoted as Q, is generated by the heater and it flows outwards through both slabs. On the left side, we have QA through slab A, and on the right side QB through slab B. The ambient air temperature on both sides is TA, and we have heat transfer coefficients H1 and H2 on the outer surfaces. The diagram also shows the thicknesses of the slabs LA and LB and the temperatures at various points T1 and T2. Let's detail the problem statement. A square plate heater measuring 15 by 15 centimeters is positioned between two slabs. Slab A is 2 centimeters thick with a thermoconductivity of 50 watts per meter degree Celsius. Slab B is 1 centimeter thick with a thermoconductivity of 0.2 watts per meter degree Celsius. The outside heat transfer coefficients are 200 watts per square meter degree Celsius on side A, H1, and 50 watts per square meter degree Celsius on side B, H2. The surrounding air temperature is 25 degrees Celsius. If the heater's rating is 1 kilowatt, we need to find two things. First, the maximum temperature in the system, and second, the outer surface temperatures of both slabs. Now let's list the given parameters for our solution. The thickness of slab A is 2 centimeters. Slab B is 1 centimeter. Thermoconductivities Ka is 50. The overall heat transfer coefficients H1 is 200 watts per square meter degree Celsius, H2 50 watts per square meter degree Celsius. The area of the plate is 0.15 multiplied by 0.15, which gives us 0.0225 square meters. The rating of the heater is 1 kilowatt. Finally, the temperature of the surrounding air TA is 25 degrees Celsius. Our first task is to find the maximum temperature in the system denoted as Tmax. For steady state heat flow, the total heat generated by the heater Q must be equal to the sum of the heat flow through slab A, QA, and the heat flow through slab B, QB. Each of these heat flows can be expressed in terms of the temperature difference and the total thermal resistance of the respective path. Now, the total heat generated Q is equal to the temperature difference, Tmax minus TA, multiplied by area, and then multiplied by the sum of the inverse of the total resistances for each path. The resistance for slab A includes its conduction, a resistance LA over Ka, and the convective resistance 1 over H1 times A. Similarly, slab B, its resistance includes LB over KB and 1 over H2 times A. We can simplify this by factoring out the area A and the temperature difference, Tmax minus TA. Please note that the formula on the slide has a slight simplification where the area A is already incorporated into the resistance terms, effectively representing resistances per unit area. Now, let's substitute the numerical values into the equation. And once we do that, after calculating the terms within the brackets, the equation then simplifies so that we end up having the value that is shown there, and rearranging and completely solving the equation, we find Tmax is equals to 247.8 degrees Celsius, and this is the highest temperature within the entire system, occurring at the interface where the heater is located. And next, we need to find the outer surface temperatures of the two slabs T1 and T2. Let's start with T1. the outer surface temperature of slab A. The heat flow through slab A, QA, can be expressed in two ways, either as conduction from Tmax to T1 or as convection um, from T1 to the ambient air, TA. So QA equals Ka times A times Tmax minus T1 divided by LA. This also equals H1 times A times T1 minus TA. Now we can equate these two equations and cancel out the area A, and substituting the known values and expanding further, we end up with the value of T1, which is equals to 231.3 degrees Celsius. This is the temperature of the outer surface of slab A. Similarly, let's find T2. The heat flow through slab B, QB, can also be expressed as conduction from Tmax to T2 or as convection from T2 to the ambient air, TA. Okay. Again, we equate the expressions, cancel out the area A, and then by substitution and simplifying the equation, we end up with a value of P2 equal to 88.6 degrees Celsius. This is the temperature of the outer slab surface B. This concludes our solution for example 3. Thank you for watching. If you found this video helpful, please consider subscribing to our channel for more content like this. Don't forget to hit the notification bell so you don't miss out on our latest uploads.